Hello and welcome back to Math 100. We are now ready to finish our chapter 5 by studying section 5.5. Remember, chapter 5 was all about statistics. All right, so we are going to finish this with one of the crowning achievements of the discipline of statistics, normal distribution. Okay, sometimes called a Gaussian or bell-shaped distribution. And this is typically the kind of graph that you saw that's kind of bell-shaped. And it turns out that this normal distribution actually can tell you a lot. And we will especially study this from the standpoint of how to find percentiles, okay? So this will tell you, like, relatively speaking, where are you standing in terms of things like your SAT score or your IQ level or your credit score and many other things. All right, so let's look into normal distribution, section 5.5. The last of the 5 sections of chapter 5 has the title normal distribution. There is a one specific type of normal distribution called the standard normal distribution, but that is something that we will look into later, okay? Let's see, the main question here is, what is the bell-shaped curve, the normal distribution, and what is it used for? Who uses normal distribution? And the answer may surprise you, but pretty much everybody, okay, directly or indirectly. People or the business decision makers who decide what to, what area to go into or where to build a building. They study the traffic patterns, and then what they normally come up with is some sort of a normal distribution. Based on what they see, they may decide where to build a mall or where not to build a mall. Your doctor may prescribe medication based on what percentile you are in terms of your blood pressure or blood sugar level or cholesterol level. Okay, schools, colleges may decide on your admissions based on your SAT score. They don't do that anymore, at least in the UC system, but it may be based on the percentile, which is actually reflected in your SAT score and so on. Okay, so again, let me just emphasize this. You may not be aware of this, but normal distribution is extensively used in many, many areas of our society. Okay, so here are the notes. Normal distribution, also called, there are many other ways to call this a bell-shaped distribution, but another typical name for this is Gaussian. Okay, this is named after a mathematician named Carl Friedrich Gauss, a German mathematician, sometimes called the Prince of Mathematicians or Titan of Mathematicians. He's probably one of the most famous mathematicians of all times. He did lots of mathematics, applied and pure, plus he was also involved in astronomy, physics, and many other things, including statistics. And so this bell-shaped curve is named after Carl Friedrich Gauss and sometimes called the Gaussian or Gauss distribution. The most common and the most popular and the most important probability distribution. All right, so the curve is bell-shaped. I don't have to say this again, but it's bell-shaped and what? And one important thing here, it's symmetric, okay, which means the left and the right-hand sides look exactly the same. The mean and the median are in the middle, okay? And so that means 50% of the data are on the right and 50% are on the left-hand side of the middle line. And what you're seeing now on the screen is a typical bell-shaped curve representing the normal distribution. Now you see sort of a funny looking letters here. These are Greek letters. Mu, remember in the previous section, we learned that mu represents the arithmetic mean or the average. And then you have the sigma. Remember, sigma was a standard deviation. And mu plus sigma then is the number or the value, which is one standard deviation above the mean, right? This is the mean. This is one standard deviation above the mean. This number here, that's mu plus 2 sigma. That would be 2 standard deviations above the mean. And this is 3 standard deviations above the mean. On the left-hand side, similar. Mu minus 1 is the value which is 1 standard deviation below the mean, and so on. Okay, and underneath of this, everybody, all the scores are included underneath of this bell-shaped and symmetric curve. Many quantities are normally distributed with a mean. Oh yeah, I guess I can't write this because my typewriter, without changing the settings, could only type in English. All right, so the mean, remember this is mu, and the standard deviation is sigma. All right, my handwriting in Greek is not very good. I did not go into a fancy Greek calligraphy school, so that's okay. But the mean is indicated by this Greek letter mu, and the standard deviation by sigma, lowercase sigma. All right. If you are to look in the back of chapter 5 in your textbook, okay, and this is not really technically a part of section 5.5, but if you look at the back of chapter 5, section 5, and after all the exercises, there's a little section called for further explorations. Okay, and there you have this thing called the empirical rule. And I'm going to bring this out here now because this is really going to give you a pretty good indication of what a big picture. Okay, so what does this empirical rule say? Empirical means observational. And so when you observe a typical distribution, which is a normal distribution, then we can make some claims. All right, and so maybe I should write down what I just said. The textbook has this in the for further explorations ... section, the end of chapter 5. All right, but this is what it says. 3 statements. Okay, you see this thing here, by the way, the mean is right here. Oh, one more thing I should say, because we are talking about the a particular type of distribution, which is a kind of continuous normal continuous probability distribution. And continuous means you have a nice smooth graph here. We don't talk about the probability that the value is exactly one number. Okay, because we're talking about the area underneath this curve representing the percentage of all data. All right, and also, so because we don't talk about the probability that the value is exactly this one number, we don't make the distinction between less than and less than or equal to. So I'm not going to say less than or equal to, or more than or equal to. Just simply ignore that or equal to part, because we just assume that the probability of the value being exactly one number is negligible. All right, so with that, I mean, that's a technical issue. I probably didn't have to say that, but let's discuss what this is saying. All right, so you notice that the bell-shaped curve has many data values kind of toward the middle. Okay, and the the farther you go, the more extreme the numbers get, and then the number of values or the percentage of the values will get much smaller. That's why you have this bell-shaped curve that goes down, 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 you know, as the value goes to infinity. So here's the mean. And now you can go 1 unit to the right, which is 1 standard deviation above the mean and 1 standard deviation below the mean. So let me go ahead and highlight this. Okay, this part here between 1 standard deviation below the mean and 1 standard deviation above the mean. Because of the mathematics involved in this definition of this curve, we know that there are 34% here and 34% here. And that means a total of 68% of the data values are within 1 standard deviation of the mean. Okay, does that make sense? I hope it does. All right, so the first thing is 68% of all the data values are within 1 standard deviation of the mean. Okay, so that means between mu minus sigma and mu plus sigma, you have 68% of the population or 68% of the data values. Now, if you go 2 sigma, that's 2 standard deviations higher than the mean and 2 standard deviations lower than the mean. You're going to add additional 13.5% here, 13.5% here. And so if you are talking about this interval from here to here, that's a lot more than that. Okay, that's a lot more than a 68%. And in fact, you can just add up these numbers. 95% of all the data values are within two standard deviations of the mean. Okay. And similarly, if you go one more standard deviation, let's go from this point, 3 standard deviations below the mean and 3 standard deviations above the mean. If you go from here to here, that's virtually all of them. And you can add up the percentages shown in this graph, but this is the conclusion. 99.7% of all the data values are within 3 standard deviations of the mean. And that's virtually everybody, okay? And in fact, some people say that, I mean, that is virtually every value is within 3 standard deviations of the mean. And as long as you know, or you have reasons to believe that some data is distributed with the normal distribution, okay, then you can make this claim. This is called the empirical rule. All of these 3 things together is called the empirical rule, or using the percentages, sometimes referred to as the 68, 95, 99.7 rule. Okay, that's a funny name for the rule, but that helps you remember what these numbers are. So again, it says 68% of the population. Let's say this is like representing the height of all Americans. Okay, and I don't know what the mean is, I don't know what the standard deviation is, but whatever it is, as long as the heights of American people are normally distributed, which they are, then 68% of the population are within 1 standard deviation of the mean, and 95% of all the people are within 2 standard deviations of the mean, and pretty much everybody is within 3 standard deviations of the mean, or more technically speaking, 99.7% are within standard deviations of the mean. Now, there's actually, this is only with 1, 2, and 3 standard deviations, but there's actually a better and more precise percentage figures are available, and that's what the another table is going to provide. This is called the standard normal distribution table. Okay, but in order to use that, we need to know how many standard deviations above or below the mean a particular number is. All right, so let's say here's the value. Let's say that's 75 or something, or 27, whatever. Okay, that value is what? How many standard deviations above the mean or below the mean? That's the first thing you need to know about a data value before you can talk about the probability or the percentage of people below that number or above that number. I'll explain this in a few minutes, okay? But anytime you have a normal distribution, okay, because you can have different means, different standard deviation. If the number is small, if all the numbers are small, the mean could be a small number and the standard deviation could be even smaller. If you're talking about a large number, let's say mu, the average is 40,000 pounds, maybe something really heavy, and the standard deviation could be like 3,000, right? So you have all kinds of normal distributions with different mu and sigma values. But there's a way to standardize all of those, and that is the normalization procedure, and the result is called the normal standard deviation. So let me explain what I mean by that. What we do need to know is, given a data value, how many standard deviations above or below that number is from the mean. Okay, so we can normalize this, the quantity, to find the z-score. That's the key word here, the z-score of each value, which shows, the z-score shows how many standard deviations above or below the mean the score is. Okay, now I'm going to give you a formula here. In fact, I'm going to give you a formula, just handwrite the formula. I don't want you to be scared of this, okay? And in fact, it is quite intuitive how you define this. The z-score of a data value is simply going to be the value that you have minus the mean. Okay, so that's called a deviation, remember? Divided by sigma, the standard deviation. Of course, this is going to tell you how many standard deviations above the mean or below the mean that value is. Okay, so this is the value minus the mean divided by the standard deviation. All right, let me again emphasize, this is not hard. If you're scared of any formula, maybe you're allergic to mathematical formulas, this is not hard. Let me just show you. All right, suppose that you have bunch of test scores and they are normally distributed with the mu of 60 and the standard deviation of 10. You know what that means? Whoop, that's terrible. Why my, yeah, so somehow my, oh yeah, it's too bad. That's not too bad, okay. Let's suppose that this is a nice smooth curve. It isn't, but let's just pretend that it is, okay. What the information given is saying is that mu is 60. So the average or the mean is 60 and the standard deviation is 10. Remember, within 3 standard deviations, almost everything is there, right? So because the standard deviation is 10, this number will be 70. This is mu plus sigma, right? And then 80 is mu plus 2 sigma, and 90 is mu plus 3 sigma. Maybe I should write it down. This is mu plus sigma, and 80 is mu plus 2 sigma, and 90 is mu plus 3 sigma. This number 50, that's 10, which is standard deviation, mu minus sigma, and that's not 60, that's 40, and that's 30. Okay, according to the empirical rule, the 68, 95, 99.7 rule, almost virtually everybody should be between 30 and 90 if this information is true and the test scores are normally distributed. Okay, so this may help you. I mean, I hope this visualization will help you. What is the z-score for 60? So here is the score or the value and the z-score. If the value is 60, what's the z-score of 60? Well, you can plug it into the formula. It's 60 minus 60 divided by 10. That's 0, right? And that's intuitive because 60 is the mean. All right. So how many standard deviations above 60 is 60? And the answer is 0. Okay. The mean value, which is mu, is always going to have the z-score of 0 because of this equation, and because mu itself is the reference point. Now, how about 70? 70 is, as you know, exactly 10 above the standard deviation. I mean, 10 above the mean, but 10 is our standard deviation. So 70 should be 1 standard deviation, exactly 1 standard deviation above the mean. Okay, now you could use this formula, 70 divided by 60 divided 70 minus 60 divided by 10, and of course that's 1. But it's obvious that the z-score for 70 is exactly 1 because 70 is exactly 10 above 60, which is 1 standard deviation above 60, right? How about 80? Well, difference between 80 and 60 is 20, which is 2 standard deviations above the mean, right? So the answer is 2. Okay, again, you can use the formula, but you don't have to. And that's the point. All right, how about, let's see, 70, 60, 70, 80. How about 50? For 50, the standard deviation, well, 50 is 10 below 60, 10 below 60, which is 1 standard deviation below 60. So this will be -1. Okay, again, if you use the formula, this will be 50 minus 60 divided by 10, and that's -10 divided by -10. But you don't have to really worry about this. As long as you can simply, as long as this number is simple, you know that 50 is 10 below 60, and so that is exactly 1 standard deviation below 60. All right, I have 2 more here. Let's see, for 55, you do 55 minus 60, sorry, that's 65. 65 divided minus 60. Sorry, 65 minus 60 divided by 10. That's 5 divided by 10. That's 0.0. So 0.05, no, 0.5. So 0.5 is the z-score for the number 65. So 65 is your score or test score, this time the data value. The z-score of 65 is 0.5. For 73, you here, let me go ahead and do this. For 73, if you subtract 60 and divide it by 10, remember the top is 13. So 13 divided by 10, and that's going to give you 1.3. That is your z-score. Okay, so the z-scores for these happen to be 0, 1, 2, -1, 0.5, and 1.3. Basically, all it is you're asking how many standard deviations above the mean these numbers are. And the z-score is going to give you the answer. The picture, I think, will be very helpful. Now, here's the important thing here. Based on these z-scores, because we know pretty much everything about the normal distribution, the standard normal distribution, we can use a standard normal distribution table. I'll show you which one it is. You'll get an access to a standard normal distribution table from your Canvas shell and from that module for particularly for that section 5.5. But you can use this table to calculate exactly what percentage or what percent of the data are below or above a particular data value. So for instance, you can answer these questions. You know, if your credit score, if the credit scores are normally distributed with a mean of 705 and the standard deviation of 55, if your score is 760, what percentile are you in? And that kind of calculation can be done using the standard normal distribution table. So if you have not printed out or accessed the standard normal distribution table, which looks like this. Okay, this is the more precise version I was referring to a few minutes ago. And it'll tell you the percentage in decimal of this area between mu, which is the standard, which is the mean, and the z-score of 1.45. And it'll tell you, for instance, in this table, that the percentage of values between the z of 0 and z of 1.45, those two scores, happens to be 42.65% of the data. Okay, that's the kind of precision we can find using the standard normal curve and the table. All right, so make sure you access this or print this out before we go any further. And I will continue on the second part of section 5.5.